some expectation maximization kind of algorithm. And so both kind of algorithms are for clustering, which is okay. Good morning, everyone. Welcome to this week's lecture. So, so this week is about unsupervised learning. It's a bit different from the previous weeks. So I guess the previous weeks were all about supervised learning. And so this unsupervised learning is also a very useful technique. So we will cover some most important techniques in unsupervised learning this week. So for this lecture today, the aims are so mainly is about k-means clustering and also some expectation maximization kind of algorithm. And so both kind of algorithms are for clustering, which is the most important technique that when people talk about unsupervised learning, the first thing people would be thinking will be clustering. So supervised versus unsupervised. So in supervised, the objective is commonly known as like classification or discriminant analysis, class prediction, or supervised pattern recognition. So the main thing here is we know the classes of each sample of the data. And so for unsupervised learning, the difference here is we don't know the classes associated with the data. And so when we do this unsupervised learning, the objectives are normally cluster analysis or class discovery or unsupervised pattern recognition. So the main thing here is whether we are given the class labels for the data. So if we know which classes this data belong, then it becomes supervised learning. Or if that's the case, we can also use unsupervised learning for those data. But we will be having these class labels for evaluation. Or we don't know the class label at all, then for evaluation, it will be some kind of different types of evaluation metrics. Different from what you've learned for the supervised learning techniques. So for unsupervised learning, why do we need unsupervised learning? So the first main reason is most of the world's data is unlabeled, actually. So when we learn about things, sometimes we know the objects like cats or dogs, those are labeled. But many more high-level concepts, we might not really have text description of those contexts, or we don't really partition them into categories. So many such cases will be unlabeled. And also, if we are dealing with classes, but it's quite difficult in many cases to get human or labelers to classify or to provide those ground truths for supervised learning. So, for example, it might be quite difficult. So, for example, in medical imaging, we might want to classify different types of tumors, but it might be difficult to really actually label those tumors accurately. So, we will need expert annotators to do this kind of labeling, which is then very time-consuming, and also is expensive to recruit those type of annotators to give us the ground truth for supervised learning. And also the labels can be error-prone. So that means different people might have different opinions for some of the data, and then we might get inconsistent labels. And so that could introduce lots of difficulties for the learning. And so in principle, we can use any feature as the label. So it doesn't have to be classes. So for example, we might have different attributes associated with object. For example, we might just use the color of different objects as the label. or some or even the size as different labels. So those are some implicit ways of getting the label. But often we don't really know this label, and sometimes it becomes another problem even if we can use the color to do this labeling. We first need to detect those objects in the images, so that becomes another problem. We can't really do this label before we identify those objects. So there are many use cases why unsupervised learning is important. And it's good for simplifying a problem. So that means dimensionality reduction. So it means for example, we can describe an object based on quite a number of different attributes of the object. So for each object, we have multiple attributes associated, and the number of attributes becomes the dimensionality. And it could be a bit too long for the dimensionality, and we want to reduce the dimensionality to simplify the problem. So for that, we can use unsupervised learning. And I will go into the dimensionality reduction on Wednesday. And some other use cases like exploratory data analysis. So that means we want to identify some structures that is present within this set of data. And that can be used by clustering. And data transformation to simplify a classification problem, so that's similar to dimensionality reduction. And to group data instances into subsets, so that's essentially clustering. And to discover structures or to learn new features. So these are all similar to clustering kind of technique. And to keep track of concept drift over time. So that is similar to discover structure, different kind of structures, but these can evolve over time. And to learn generative models. So generative models are they typically mean Bayesian kind of models. So that involves lots of statistics or probability type of modeling. So those are closely related to unsupervised learning. So in this today's lecture, I will focus on clustering. So clustering means we want to find groups of items that are similar. So within a data set, we might have multiple groups, and so that's the nature of the data. But how do we discover there are multiple groups in the data? So that is the clustering problem. And clustering is unsupervised because the class of any data instance is not known before we do this clustering. And success of clustering often is measured subjectively. So that means we don't really have the class labels, so we can't check the accuracy of the clustering. But we will have some other algorithms or heuristics to measure this clustering output quantitatively. So I will go into some of the evaluation metrics on Wednesday. And a data set for clustering is just like data set for classification, but without the class labels. So here is an example about the objective of clustering. So in the simplest case, it can be just like this. So it's a clustering from a partition. So we just want to partition this data set into 3 clusters, and they are not overlapped. And then another case is we can have overlapping clusters. And so these here in this case, we have also 3 clusters, but they can be overlapped. So there will be kind of membership function of each data within different clusters. And there's some other representations of the clustering output. The first one, the commonly used one, will be we want to assign a probability for each data. So for example, for A, the total probability will be 1, but there are different probabilities within these 3 clusters. And then another representation is the dendrogram. So dendrogram is it's like a tree structure, and so at the high level there are 3 clusters, and then within each cluster there are subclusters. So these are some common representation for the clustering output. And how do we get these clusters? We can have 2 categories of methods. The first one is hierarchical method, and then the second one is partitioning method. So hierarchical means we can either go bottom up or top down. So that's agglomerative or divisive kind of approaches. So, and hierarchical representation is closely related to the tree structure of the dendrograms. And it's easy for visualizing the clustering output. And partitioning method usually requires specification of the number of clusters. So we just want to partition the data into that many number of clusters. And then during this process, we try to construct the clusters and fit objects to them. And here's a mathematical representation of clustering. So, so the input, the data, will be this n. Is a n number of elements or instances. So each instance can be just a number or a vector that represent this data sample. And the objective is we want to cluster this number of instances into this number of clusters. So each Ci is called a cluster, and the whole C is the clustering. And input data can have 2 forms. So each element can be associated with a real valued vector of p number of features. So each instance can be a vector of dimension p. And we can also use pairwise similarity data between the elements as kind of input to the clustering algorithm. So in this lecture, I will mainly focus on the first type, where we have just instances as the input, or this n here, for the clustering. And feature vectors have more information, but similarity is generic, because if we use feature vectors as the input, we will have a second step that we require computing the similarity or the distances between the feature vectors for the clustering. But if we have similarity as the input already, then we can directly use a very predefined type of clustering. And so the feature vector matrix, meaning this n, would be of this size. Is n by p, because we have n elements, and each elements have p n elements, and each element have p length, or it's n vectors, and each vector have p elements. And so, and also the similarity matrix will be n by n, because we are computing a pairwise similarity between the n number of instances. And in general, the value of n is much greater than p, and that's when we would have a good clustering output. We want to have many number of data, but for each data, hopefully, the dimensionality of the feature is quite low. And if it's low, then it's easy for us to measure the similarity or the distances between the samples. otherwise, in most cases, we will need to design some smarter ways of computing this similarity. So that were the definitions of this clustering problem. And the goal here is to find the partition of n elements into homogeneous and well-separated clusters. So the objective here is we want to have clusters, and also at the same time, within each cluster, the data should be homogeneous, and between clusters, the data should be well-separated. So these measures are all based on the similarities between the feature vectors. And so in other words, elements from the same cluster should have high similarity. And in this way, we can form homogeneous clusters. And while elements from different clusters should have low similarity, and that means they are well separated. And a note here is homogeneity and separation need to be defined. So that means we need to have certain kind of mathematical formula to define these similarities. So the simplest case would be just Euclidean distance. So we just compute Euclidean distance between two vectors, and that becomes the similarity measure. And then based on that, we can evaluate the homogeneity and separation. But in many cases, simple Euclidean distance doesn't work very well. So we can have another step of learning-based similarity measure. So that in most cases actually becomes a supervised learning approach. So if we do clustering, we can have some kind of mixture between supervised and unsupervised learning, and then that will give you a better output, but it becomes more advanced technique. So I will not go into the distance learning or the learning for the similarity matrix in this week. So we will just assume all the similarity measurements are done by Euclidean distance. And also note, typically there are interactions between homogeneity and separation. That means if we have highly homogeneous clusters, in most cases, it will also lead to very low separation. So that's just because all the data are quite similar to each other. So if each cluster becomes quite similar, then there's also a high similarity between clusters. So that's just unfortunate nature about data that's often occur in most cases. So that's when we will need to design some kind of more intelligent algorithm for the clustering. So this is an example about bad clustering. So, and you can see, assume we have these two clusters, and then between the two clusters, there's only very little gap for the separation. And then within the cluster, all data are quite separated. Actually, they have quite large difference between this data. So this is just not a good way of clustering this data. Then a better way is actually the same set of data as the previous example. So a better way is we just cluster this set as a cluster and this set as another cluster. So it becomes these two clusters. And you can see now we have better separation, and within each cluster there's better homogeneity within each cluster. Then the objective here will be how can we get this kind of clustering output rather than the previous case. Then a very simple algorithm is the k-means clustering. So you probably have known this in some other lectures. So k-means is K here means the number of clusters, And to achieve this k-means clustering, first we want to initialize a set of points that are the centers of the k clusters. And so each center is a vector. So if the data is of dimensionality p, then the centers of the clusters would have the same kind of dimensionality. And we need to choose k centers corresponding to the k clusters initially at random. And then based on this random number of random centers, we can assign each instance data x to the closest of the k points. And the output will be we have k clusters. And the closest is measured by the Euclidean distance. So just check the distance between the x and the center, and then we compute a Euclidean distance, and whichever center that gives the lowest distance, then we just assign the x to that center. And then once we assign all the data, then we get these k clusters. So that is just one iteration. And then based on these k clusters, we can recompute the means of each cluster. So we just compute average value of all the data within one cluster, and that gives you a new center of that cluster. And then we can just do this computation for all k clusters. Then you have the then we have these k clusters, the new means of the k clusters. And then we can repeat steps 1 and 2 until convergence. So convergence means we have a reasonably stable clustering. And reasonably stable means we don't really have much change across iterations. Or if we can just specify number of steps or number of iterations, and then we can just stop the clustering. So here is an example of two clusters. If we have so instead of vectors for each element, we can just use numbers for the example here. So so assume we have all these numbers, and then in this example we have partitioned them into two clusters, so A and B. And so here we are visualizing this clustering output. So if we have more data around here, then we have a larger value here. That just means we have more data around this region. And so you can see there's some kind of overlap between these two clusters. And then for each cluster, there's a mean value and also a standard deviation. So we're just approximating these clusters with Gaussian functions. So that's another way of representing this cluster output. So in order to have these Gaussian curves, actually it involves the Gaussian mixture model. So so that is, normally we don't really do this simply by k-means clustering. We will need the expectation maximization algorithm that I will cover in the second half of this lecture. And so this example just means, so in some cases, we can have overlapping between these two clusters. And k-means clustering, so just another summary of what k-means clustering is. So it is a cluster that we want to partition the data based on the distances. So assume Pi is the cluster assigned to element I, and say J is the centroid of the cluster J, and D is the Euclidean distance between feature vectors V1 and V2. So the goal is to find a partition that can minimize this error, or the total distance function. So we are computing the total distance for each element. So I from 1 to n for all the n elements. And for each element, we want to find the distance between its own feature vector I and the centroid of its cluster. So assume now I is partitioned into Pi, then the centroid is CPI, and the distance is just this equation here. So the total sum should be minimized when we get this best partition or the best clustering. And centroid is the mean or weighted average of the points in this cluster, and k-means is an important clustering method. It is widely used in many different areas, and it can be viewed as a special type of technique that belongs to the expectation maximization algorithm. And there's another implementation of k-means. So previously we said we want to assign all the data points into different clusters based on the shortest distance. And then once we have the clusters, we can recompute the mean, and then do another iteration of this assignment. And another implementation is we can use, so the step 1 is the same. We still have arbitrary partition of k clusters, and then we can just check for each element I, and we find the cluster that gives a closer distance than its current cluster, and we just move this element into that cluster. So that's another more like stochastic kind of implementation for the k-means clustering. And here's an example of the effect of k-means clustering. So we have, so initial partition is annotated by this number 1. So with 1, we have 3 clusters. And then based on the clusters, we can check the mean or the centroid of the clusters. And then we can move the cluster to its current cluster centroid to its current position here, and then we get this colored centroid here. And then based on this, we can do another partitioning of the data, and then we get this step 2 clusters. And then we do this computation of the centroid again, and then move those centroid to these 3 points, and then we do this partitioning of the data again. So it's an iterative approach that gradually gives us a better partitioning among this data. And in this case, we have x1 and x2 here. So that means for each data instance, we have 2 elements. So that's a dimensionality of 2 for this data instance. And normally we use 2 because it's easy to realize. We can just draw all the points on this coordinate system, and then can easily see the distances between the data instances. But in reality, most of the time, this dimensionality of the feature vectors will be much higher than 2. And for those, we can't really visualize them in a multi-dimensional space and how close these data are. So, and that's also affecting how we want to compute the distances between data. So that will cause lots of difficulties in the clustering algorithm. And so one way to deal with this kind of difficulty will be dimensionality reduction. And I will cover some techniques for dimensionality reduction on Wednesday. And so here, just want you to remember, here x1 and x2, they indicate the different elements in the X. So in this diagram, we don't really have a class label associated. It's all just data. And so previous diagram shows 3 steps to converge when we have 3 clusters, k equal to 3. And so we want to minimize the squared error criterion, so which is essentially the Euclidean distance. And it's a kind of approximation method for obtaining the maximum likelihood estimates for the various means. And each point is assumed to be in exactly one cluster. That means with k-means, we do this partitioning. And that's the default implementation of k-means. We don't really have any overlap between these clusters, and we don't really assign any probabilities to the clustering output. So it's a hard clustering. And so if we want to have some kind of blended clusters or overlapping clusters, a simple extension would be the fuzzy k-means. So that will give you kind of probabilities associated with the clustering outputs. Then another way is we can use expectation maximization that I will cover shortly. Here is another example. So if we have this data, and it's again x1 and x2, it's a 2-dimensional data, and we want to partition this set of points into 2 clusters. And here are the feature vectors associated with each point. And so given this data, we want to determine what are the clusters they belong to. So initially, we assign random centroid of the 2 clusters. And that's the value of the 2 centroids. So based on this centroid, we just do assignment of these points into the 2 clusters. So based on the shortest distance, these ones are closer to this center, so they all belong to cluster 1, and these belong to cluster 2. And here we do this allocation, and we also updated the centroid based on the new set of clustering results. And then based on the new centroids here and here, we do this clustering again for all the data. And then we can see that these points, they still belong to the same clusters as in the previous step. So that means there's no change between iterations. So we get a stable clustering output, and then we just stop here with just 2 iterations. Then we get this clustering output. So in this example, we just show we require initialization and some iteration steps. And this clustering found the solution after a single iteration, and the algorithm will not change on further iterations. And by inspection, we can see the solution is good clustering, in the sense that we have 2 natural clusters in the dataset. But in general, the quality of the solution will depend on the distribution of the points, and also the choice of k, and also the choice of the initial centroids. So for example, if in this case, we can see there are 2 clusters, But if we specify a k value of 3, we will get some pretty funny clustering outputs. But in many cases, for real life dataset, normally we don't really know how many clusters should be there. So that would be some kind of difficulty in applying this kind of clustering algorithms. So here in k-means clustering, the most important parameter will be the number of clusters, the value k. And so in order to show this, so for this example, we still use x1, x2, and then assume we want to have 3 clusters from this output. And then the clustering output would probably look like this. We have a cluster there, another cluster, and another cluster. So and then the k-means run by, we have initial centroids, and then do initial partitioning based on the centroids, and then we update the centroids and do another partitioning, and then that's after iteration number 20, we get these outputs. So here, that's probably the best we can get with 3 clusters. But if we look at this data, we might think actually it would be better if we just use 2 clusters. 1 cluster here, another cluster here. So that will require some kind of experimental design, and especially if we can analyze from this problem how many clusters we should have, then we will expect some kind of better outputs. And here is another problem. So in addition to the setting of the parameter k, there's also sometimes we are really affected by outliers. So outlier means we have just a very extreme number here, and all the other elements are here. And if we do this distance computation by including all the data, this will be the kind of clustering output that we will get. We will try to find a centroid that minimizes the distance between these instances, and then another centroid here, and then the total distances will be minimized by assigning these 2 centroids, and then these will be the 2 clusters that we get. So obviously, this will be another better cluster. We just reject this data as the outlier, and then we use the other samples to generate the 2 clusters. And this is often occurred in actual real data sets. With some kind of measurements, it's easy to get outlier. And then when we do clustering, we should try to avoid the influence from the outlier. So in order to achieve this kind of output, we need to have some techniques to deal with outlier. And then the first simple technique is we try to remove those data points that are much further away from the centroids. So we can just check where most data are located, and then just discard those data that are very different from the rest of the data. And to be safe, we may want to monitor these possible outliers over a few iterations. So if after a few iterations we are quite sure which are the outliers, then only then we remove those data. Otherwise, we will keep them there for a few iterations and then see how the outputs will be. And another way is we perform a random sampling of the data. So that means we don't want to do this clustering for the entire data set. We just choose a small subset of the data, and then based on the subset, we do this normal k-means clustering. And then once we have the k number of clusters with the centroid, we just fixed the centroids and then assign the rest of data into these clusters. So this is a quite intuitive way of dealing with the cluster outliers. And similarly, we can also do this multiple times in order to make sure that we are not biased by the initial subset of the sampling. So here is another example that is to show that our initialization of the cluster centroids are also important. So we are not demonstrating the number of clusters anymore, and assume we know there are 2 clusters, but how do we set these initial Cs or the initial centroids is quite important for the output. So if we have the 2 centroids here, then after 2 iterations, we would have these 2 clusters. And if we have the initial centroids here and here, then we would get a much better clustering output. And often, once we get some kind of output like this, we are not able to recover or improve it anymore. So because they are quite stable there. If you compute the distance between the centroid and all the data points, these are the ideal partition of the data already. So you won't be able to see any further update of the clustering or the centroids. So that is the final output you are going to get. And then you are not going to recover a better option like this. So that is one of the main issues with k-means clustering. The initial points of the centroids are very important. So that's why if you use k-means clustering, even if you use some existing package, standard package, internally, there's always some kind of multiple trying of this k-means. They want to do this k-means clustering multiple times and then try to find the better option among these multiple iterations. Yes?
I do understand that why are you trying to identify the outliers here, but the sentence doesn't look to be correct here, because many times we do clustering analysis because we want to identify some of the outliers purposefully. For example, in financial crime, we would want to understand that certain credit card transactions are actually outliers, which may be a certain reason for financial institution to take action against those outliers. So I just want to highlight here that this particular sentence that remove the outlier will not always be correct, because you would want to carefully evaluate those outliers before you remove them.
Yeah. Here the objective is to remove, but there are many cases we can, for example, in this case, if you just increase the number of clusters, we just say we want, instead of 2, we want 3 clusters, then those outliers will become another cluster. So that will be another way of dealing with outliers. So so there's lots of experiments. Yeah. Yeah. And it doesn't mean you just need, it doesn't mean one outline cluster will be enough. It could be multiple. So that's why you need to try multiple iterations with the number of clusters and also the initial points for the centroids. Yeah. So that's another example. So assume we have this kind of data. It's a toy example. So assume we just place 4 instances, so at the vertices of the rectangle. So these 4 points represent the centroids of the clusters. And once we have these centroids, all the points along the edge of the rectangles will be allocated to the nearest 2 clusters. So, so we would have 1 cluster here and 1 cluster here, and along the long edges, for example. So that is not ideal. We would want to have a cluster here and a cluster there, so there's better separation between the 2 clusters. So this is just to show you similar to this one. So if once we have non-ideal initial points, we wouldn't be able to generate a better cluster. And so results vary significantly based on the initial choice of Cs. Simple way to increase the chance of finding a global optimal will be just restart with random Cs multiple times. And this can be time consuming. And another way is k-means plus plus, which initialize k centroids to be maximally distant from each other. So there are multiple algorithms how we can choose better initial centroids. And so if you are interested, later you can just do a quick search online. There are many ways of doing this. And normally in the all the libraries, there will be different options that we can choose to specify the initial centroids. And we can just try with different options and see how it works. Yes? It should be, because k-means is a hard assignment of the data. So GMM has a better accommodation of the properties within the feature space. So we would expect a better result from the GMM. But then, of course, we need to assume the points actually follow a Gaussian distribution. And it might not really be the case. It does happen quite often, yeah. But with multiple restarts, we can easily resolve it. So a short summary of the k-means. So despite all the weaknesses, k-means is still the most popular algorithm due to its simplicity and efficiency. And so for other clustering algorithms, it depends on the use cases or the applications that you want to try. Some other algorithms might give you a better output, but in general, they don't really prove a very big advantage over k-means. So for example, there are spectral clustering or other clustering, and so they can perform better in certain applications, but we don't really see a big difference in all. So in general, you can't really tell which one is better, especially because it's difficult to evaluate the performance of clustering. And no one knows which ones are the correct clusters, especially when the data set has high dimensionality. And here are some just simple examples about how we can use the k-means. So the simplest one will be we can use k-means clustering for image segmentation. The segmentation means we want to partition the pixels into homogeneous regions. And in this case, homogeneous just means similar colors within the region. And for example, for this one, we would want to have a region for the yellow part, another region for the blue part, and then multiple regions on the boy. So if we choose k equal to 2, this will be the output. And this might be what we want, actually, and depends on the use case or the user requirement. And we can then vary the value of k and see what's the output and whether it's something that we would expect. So if you have the k to be really large, then the segmentation might be very fine level, which might not be our expected result anymore. So so when we use k-means for segmentation, it's really a user-specific kind of use case. And another example is this is a commonly used technique in computer vision and also in natural language processing. We want to do a bag of words. So that means we want to classify or cluster the various patches in the image into different categories. So so if this one we just partition the image into very small patches, and then for each patch we can extract a feature descriptor, for example the SIF descriptor, which is a high dimensional feature vector. And then we can just do a clustering of all the feature vectors into multiple clusters. So for example, we just do 3 clusters for all the patches. Or in this case, we are using these small regions to represent the patches. And then for each cluster, we have this centroid of the cluster. And that centroid becomes the visual vocabulary of the cluster. So a vocabulary means just abstract representation of some kind of features within the image. And in this case, we just want to detect 3 words within this vocabulary, or 3 types of features within this image. And these are some examples. So these are, each one represent a cluster centroid. So just we convert back into image form and just for a simple example. And in this example, assume we have this many number of visual words in this image. So that means we have this number of clusters of the patches within this image. And then we can compute the number of patches that belong to each cluster. And the number of patches belong to each cluster becomes the frequency of the occurrence of that kind of feature appeared in the image. And if we accumulate all the frequencies into this kind of representation, it becomes a histogram of the visual words in the image. And then this histogram is essentially a vector. So in this vector, we have this many, like for example, 10 or 12 elements in this feature vector, and then each element has the frequency as the value. So that is the feature vector that we can use for further processing. And for example, we can use this for image retrieval. So we can represent this image by the histogram feature. And then we do image retrieval, so we want to find images that have the similar kind of histogram representation. So, so to do this, we just do this histogram computation for all the images, and then we do a distance check between the histograms, between 2 images, and then we find images that have smaller distances, and then that means more similar images, then we can just show those images as the retrieval outputs. So that is an example of how we can use the K-means clustering. Okay, we will have a short break, and then I will cover this expectation maximization.
cluster 分配一个中心，那这个中心是一个 sample 是一个 instance 还是说是一个随便一个题？就它可以不是某个 instance。就随便选一个题，它也可以不是那个数据集里的一个题。那这第一步是这一步是在说。所有的所以一个点分，离谁最近分离谁。然后再根据第一次的分配的结果，再去计算它的中心，然后再根据这个中心再去分配这个中心，直到我们这个数据。这个算法，第二步有点看不太懂，就是。
这个还不是最大的问题，因为时间它有24小时，还是比较清楚的一个东西。但是后面还有一个位置，就是这样很多个位置。对，这种没有，它有非常多，就是每个 sample 对应的非常多个位置，我要怎么把它们整合起来？因为我想不出来一种方法把它整合起来。比如说比较专用的，就是说，比如说，就是有很多个，每个 sample 对应的很多个向量，然后把这些向量整合成一个 feature 出来。这个位置，我本来时间我是想把它做成那个24个 vector 的，但是这样的话，就是感觉会就是有一个 assumption，就是说，比如说0点和12点的时候，时间就是那两个特征是相反的。我觉得这不大好，最后才做了我好的 encoding，但是位置我实在找不到一种方法去表达它。
你不是用 regression？
是要用 regression， 但是它有非常多的。example 对应的一个 CSV 表格，一个 CSV 表格里面。那我们要稍等。
然后咱们
是这样子的，这算是第三个数据。然后，对，这样很多人不是但是它是每个学生的数据。这是对啊，但是它这个只有每个学生都但是想位置 average 的话，它不会丢很多东西。
现在是咱们举的是看起来是不是比较不是很好？因为我的意思是说 correlation 不是特别大，这块按道理来说应该是那个结果的，就是看起来不是特别大。它如果多个feature结合起来玩，它会更好一点吧。 为什么这么说？是你描述出一个根跟叫
Okay, so let's continue with the lecture. Okay, expectation maximization. So this is used when data is only partially observable and is also often used in unsupervised learning and sometimes for supervised learning as well. But then in supervised learning, when we use expectation maximization, it's because we have some attributes that are not observed. And then we formulate this supervised learning in an expectation maximization kind of framework in order to overcome these unobserved variables. So I will explain shortly about what unobserved variables mean. And there are some use cases, like we can use EM to train Bayesian belief networks, and we can use EM for k-means clustering, or it's not exactly k-means clustering, but with similar kind of objectives. And it's often used in hidden Markov models as well. So here, these are more advanced concepts. I will just mainly focus on how to use EM for clustering. So the first most important concept that's related to expectation maximization is we have finite mixtures. So mixtures means we have a set of Gaussian functions, and there are overlaps between the Gaussian functions, and then in this set, it becomes a mixture between these Gaussian functions. So that is what finite mixture means. And it's called finite because we know the number of Gaussian functions. So it is not infinite number of mixtures. And so when we generate this finite mixture, we do this by choosing one of the k Gaussians with uniform probability. So uniform probability means there's equal probability that we can assign to these k Gaussian functions. And then once we have one Gaussian function, we can just do the sampling based on the Gaussian function. So Gaussian, we have x and y, then we just do the selection of the x based on the shape of the Gaussian. And so here is an example. So in this one, we have two Gaussian functions. So for each one, we have the x-axis represent the data, and then the y-axis is the px. So that's the probability of that particular data, and the probability follows this Gaussian function. And in Gaussian, we have, to describe a Gaussian function, we have the mean and the standard deviation, and also the magnitude here. Normally we use it as another value of probability for that Gaussian. So if we have a distribution, and if these two have equal probability, then each one would have just a 0.5 probability. And then we only care about the mean of the Gaussian and the standard deviation. So these two variables would fully quantify this Gaussian function. And here is this example again. It's the same slide that I show for the k-means clustering. So it's better explained if we consider this Gaussian mixture. And so we have this set of data, and assume if we know which cluster they belong to. So if we have two clusters and we know whether they belong to cluster A or cluster B, then based on this table, we can generate these two Gaussian functions. Because we can just check what's the mean value of the cluster A, and what's the mean for cluster B, and what are the standard deviations of these two clusters. And then we also have the probability of A. So we have 60% of the data belong to A and 40% belong to B. And then, so that's the PA, PB here. And then for the mean of A is around 50, and mean of B is around 65. And we can check the frequency, actual frequency of the data happening around the mean. And then we get all this magnitude, and we have the standard deviation as well. So based on the table, we can generate this Gaussian mixture. And then the problem is actually the reverse. So assume that we know this data belong to two Gaussians, but we don't really know which Gaussian each data belongs to. So this column, all the assignment of the clusters are not known actually. So we only know the numbers. But then if we actually know the functions of the Gaussian, so if we know the first Gaussian has a mean around 50 and the second one around 65, then we can easily allocate these data samples into these two Gaussians. And and when we do this allocation, we can also have probability. So because, for example, for data here, it can belong to A and also belong to B, but it's just there's much lower probability if this data belongs to the Gaussian B. So when we do this cluster assignment, if we use Gaussian mixture, we are using probabilities for the clustering. But then actually we don't even know what are the two Gaussian functions. So we don't have any information here and not any clustering information here. Well, what we have are just the numbers. So how do we come out with this clustering and also this Gaussian mixture model here, just based on the numbers? And so that is essentially what we can use, or we can achieve by this expectation maximization model. So if we formulate this expectation maximization mathematically, so here are the definitions. And what we are given are instances from X, so that's the data. And assume that this data were generated by the mixture of K Gaussian distributions. So, and this assumption is there just to make sure that we can actually partition this X into various Gaussian functions. So it follows the Gaussian distribution. And we know that there are K Gaussians, so the number of clusters is known, but we don't know what are the means of the K Gaussians. So and also we don't know the standard deviations of the Gaussians. And we don't know which instance X was generated by which Gaussian. So we don't know the actual clustering of the data. So all we know are just the feature vectors of the data, and we know they are K Gaussians. So what we want to determine here are these mean values of the K Gaussians. Once we have these mean values, we can easily allocate all the data into the various Gaussians with probabilities. So this is the objective for the expectation maximization problem. And here's an example about the fitting of a Gaussian to the data. So if we have this data that's represented by the bar chart, that's the data. And if we just use one Gaussian function, that's what we are going to get. So use this one to fit into this model. And so it's not that ideal for the fitting. And if we use two Gaussians, we would get much better approximation of the actual data using these two Gaussians. So there's actually overlap area here, around here. So and you sum them up, you would get this curve here. And so the y-axis here is the probability, and the x-axis is the value of the data. And here it's just actually a one-dimensional value. And if we have high-dimensional feature vectors, then we can't really visualize this very well. But it doesn't matter how big the dimension is. We can always use Gaussian mixture models. And so think of full description of each instance as this yi. And so that's the full description of a data sample. Here, xi is the feature vector of the data, and zi1 and zi2 are two unknown variables, or we can call it latent variables. So zi1 can be either 0 or 1. So 0 means xi doesn't belong to Gaussian 1. And if zi1 is 1, then it means xi belongs to Gaussian 1. And similarly for the I2, so if it's 0, that means xi doesn't belong to this Gaussian function. And if it's 1, that means xi belongs to this. So we are using zi1, zi2, just assume we have two Gaussian functions in this model. So we can summarize this as zij, and j would be the index into the various Gaussian function. And then this zij here is the unobserved variable. So that was what I mentioned in the first slide for expectation maximization. In this kind of models, we always have some elements that are observed. So that's xi. We know the value of xi. And some variables that are not observed. So that is, in this case, is this zij. Here, we don't really know which Gaussian function this xi come from. And so the instance set here is the set of xi, and these are observed, and then zij are the unobserved values. So this is the full description of the input to the expectation maximization. And so now we just show a simple algorithm for how we can estimating this k-means clustering using expectation maximization. So first, we still choose a random set of mean values for the Gaussian functions. Also assume we just have two Gaussian functions in this mixture model. So what we want to have are the two mean values, mu1 and mu2. They are defined as h. And then we iterate through two steps. The first one is E step. So E is this E here, so that's the expectation step. We want to calculate the expected value of this E zij of each hidden variable zij, assuming current hypothesis H holds. So that means assuming this holds just means assuming we know this H. And then we know X, so we can compute zij. So here, Zij, the expected value of Zij, so that means some estimation. And we use the probability computations here. So probability of xi given mu j and divide by this sum of xi given mu n, and n is from 1 to 2. So this term here is just the total probability of xi belong to either Gaussian 1 or Gaussian 2. And then here is the probability of xi belong to the Gaussian j, and j can be either 1 or 2. So, and because this probability, we can just plug in this Gaussian function, and the Gaussian function gives you a probability. And sigma here is actually also unknown, but in this very simple algorithm, we just assume sigma is known. So that's the standard deviation of the Gaussian. And then here, since we assume mu1 and mu2 are known as well, so this equation can be derived. We can get actual value from this equation, and that's the probability, and that gives you EZij. So we get two values essentially. It's EZi1 and EZi2 from this computation. So this expectation step gives you the probability of this x belonging to either Gaussian functions. And then the next step is this maximization step. So the objective is to get this actual, so it means we want to update this hypothesis so that we can maximize the total probability. So it's calculating the new maximum likelihood hypothesis H prime, and assuming value taken on by each hidden variable Zij is the expected value calculated before. And then we can just replace the previous hypothesis H by H prime. And so H prime is this mu1 and mu2 prime, and we can do this computation using these equations. So this one is essentially a weighted average of all the variables, all the data for each Gaussian. So E here is the probability and of xi belong to j, and we use the probability as the weight value to time with this data, and then divided by the total probability. So it's essentially this one, and so that's just a weighted average based on the probability of all the data samples belonging to that particular Gaussian. And then because this is a mean value, so that's why we want to do this weighted average for that Gaussian. So the maximization step gives you the unknown parameters of this EM's algorithm. The unknown is although we also don't know Zij, but this is kind of latent variable or the intermediate variable. The actual main important variables are these mean values of these Gaussian functions. So that's what we want to derive at this maximization step. And then we can iterate. Again, we go back to the expectation step and use the new H prime as these two variables here, and then compute the probabilities again. And so it's similar to k-means clustering. Yes?
When you maximize, do you maximize the expectation on the each point, or on the like, sum of the
Um,
have this expression of data which is, okay, this point belongs to that cluster, and this point belongs to that cluster. And I might maximize both of them, I might, like, what are we actually
we this one is actually deterministic. We are just using the probabilities that we got from this one to do this average. So what we are maximizing is the total likelihood or the probability of having those points within this particular Gaussian function. So it's not maximizing for each point. It's maximizing for this Gaussian function.
I guess the maximum likelihood, like total likelihood of the
Yeah, yeah.
turns out to be a maximized expectation.
Yeah. So it's a maximum likelihood for the mean, actually. That means so it's most likely the mean of the Gaussian function will be here after this step.
Care about actual point, actually care about maximizing.
Yeah. The overall structure of the data. So yeah. So the E step is to calculate probabilities for unknown parameters for each instance. And then the M step is to estimate parameters based on the probabilities. And then the parameters here mean the means of the Gaussian functions. And so in k-means, the probabilities are stored as instance weights. So that just mean we have the occurrences of the data belonging to different clusters as the probabilities. So that's one view of viewing this k-means clustering. But in EM, we produce soft assignments or probabilities of data points into clusters. So that just means in EM, this step is very important. For each data, we have two probabilities representing the data belonging to two clusters. So we are not assigning the data into one specific cluster anymore. Like k-means, we can only assign the data into one cluster. But here, we are assigning it to all the clusters, but then we have different probabilities of having the data into different clusters. So that's with this probability, we call it the soft assignments. And EM can converge to local maximum likelihood. Ideally, we want to have a globally maximized parameters, but in effect, actually EM will converge to a local maximum likelihood. So and this H also helps to provide estimates of hidden variables that ij. And another definition of this EM is this using this kind of annotations. So we have the probability of y, so that's data, and given the parameter h. And we do a log computation mainly just to make the mathematics convenient, because Gaussian has exponential function, so we can do a log. And so that's give you the expected value of this probability. And y here is the data, which is the complete data, and that includes both the observed value, so that's the feature vector input of the data, and unobserved variable. And in the case of clustering, the unobserved variable is the cluster assignments, Zij. And expected value taken over possible values of unobserved variables in Y is what we use to get this this computation here. So that's also when we talk about EM initially, that's how EM can accommodate unobserved data, is why these iterative steps we can just assume some values for the the parameters, and then based on the parameters, we can check the unobserved variables, and then we can update these parameters. So it's like alternating between two steps that can help to incorporate these latent variables into this model. And this is just an example of how we can use EM to do clustering. The output actually look very similar to how what we will get from k-means clustering, but it's just using EM to do this clustering. So we also start with a random initialization of the cluster centroids, and then we can do EM steps alternatively, and finally we would get this final clustering output. So it's all probabilities. So now when we do the actual final assignment, we just assign the data to the cluster with the highest probability. Here is a better example about the difference between k-means clustering and EM clustering. So that's the original data, and that's output from k-means clustering. That's output from EM clustering. So we can see that this EM clustering gives you the better cluster than the k-means clustering. And here, there's some actually some outliers. And in this data, because we are just using 3 clusters, so that will be what we get from the clustering output. And so this one performs better, mainly because of this self-assignment with the probabilities, and then this weighted average and probability computation can help to make some of the data samples better clustered. Yes? Sorry? Yeah, that's based on some definition of the problem. So, for example, they might belong to different species, and then different species can have different properties of some kind of variables. So we're just using a 2-dimensional data to represent this data. Okay, so extending from the previous model, a simple extension will be we want to use more than 2 distributions. That's not a problem. The algorithm, the pseudocode, can be easily used for more than 2 distributions. And we were also assuming, so in the previous example, we were assuming there were just 1 element in the feature vector. And then because the Gaussian function was plotted for a 1-dimensional data, actually, only the x-axis is the value of the feature vector. So that was 1 attribute per data instance. So that's not normally how it is actually used. So typically we would have a multi-dimensional feature vector. So that would mean several attributes. And to extend this mixture model to more than 1 attribute, it's easy if the attributes are independent among themselves. So that means if we have 10 elements for each data vector, all the 10 elements are mirrored independently. There's no correlation between the feature values. Then we can just use Gaussian mixture, kind of the same probability computation for each element, and then we can just multiply all the probabilities of the 10 elements together to get a final probability. So that's one way of doing it. So we are treating the elements or the attributes independently, and so that's quite easy to do. But if it's correlated attributes, means there are some correlation between the elements of the feature vectors, we don't don't really want to handle all these elements independently. So a better way would be we can use multivariate model, and then we can, for this multivariate model, we can also use bivariate normal distribution to represent this model. And then we would have some kind of covariance matrix. So in a 1D Gaussian function, we have this sigma, or the standard deviation of the Gaussian function. And then when we have a multivariate model, we don't have this sigma anymore. We would have this covariance matrix. And that is a square matrix that store, you can think of it as it's a square matrix that store all the sigma values in the matrix. So that's sigma between each pair of element or attributes. And then if we have n number of attributes, then this square matrix will be of size n by n, but it's a symmetric matrix. So that means we only want to take half of the matrix as the actual parameters of this model, including the diagonal. So the unique number of parameters within this covariance matrix will be this number. And that will be the this number. So n times n by 1, n plus 1 divided by 2. So that's the number of parameters within the covariance matrix. And then we want to plus the number of means of the multivariate model. So that's the total number of parameters that we would need to estimate for the Gaussian mixture model. That just means we have more parameters now, but the whole expectation maximization method flow would still stay the same as the previous example. And so, so for Gaussian, normally we consider Gaussian as a continuous function. So it had all the axes are real numbered. But for the Gaussian model, we can also use nominal attributes. So that means we have category kind of values, discrete values within the data elements. So we can still use the mixture model, but then it becomes not a continuous function, but it becomes like histogram of the data. And then that counts the frequency of occurrences of the various values. So the same as the real-valued Gaussian mixture model is easy if independence is assumed when we have multiple nominal attributes. And for correlated nominal attributes, then we would result in this V1 times V2 parameters. So V1 is the number of attributes of the one dimension, and then because now the covariance matrix it has to be computed pairwise, so we can't really take a symmetric view of the covariance matrix when we deal with nominal attributes. And missing values are still easy, so it's still the same as the unobserved models, unobserved data in the model. So we can, as long as we can formulate it into alternating EM kind of steps, we can deal with some missing values. And some other distributions can be used as well. We don't have to use Gaussian, so we can use log normal or log odds or the Poisson distribution, which is very, very common for integer counts. And also the same problem, how do we determine the number of k? We can use cross-validation. So that means we want to do this multiple times and then choose the best k. And obviously this can be time consuming. So So that was all the formulation for EM in a Gaussian mixture model kind of setting. But this EM is not restricted to mixture models. So we don't have to do this for clustering. We can use EM for any type of problems as long as we have this unobserved data as the latent variables, and we want to optimize the setting of the H parameters while we have this unobserved data. So, and all the definitions here look very similar to the previous Gaussian mixture setting. But it's just a matter of we want to extending this formulation to other problems, not just clustering. So the unobserved data might not mean which cluster this data belongs to anymore. It can be some other definition. Depends on your problem. That's the latent variables. Yeah. Yeah. So if you talk about prior knowledge, yes.
If I give an EM, will you learn prior as a Gaussian, or will it learn prior as a discrete? I think in GMN.
Yeah. So this one is talking about in general. It doesn't have to be Gaussian. So it can be anything. I'll give you an example at the end. So then the EM method is to calculate a likelihood function and using the observed X and the current parameters H. So this definition is just we want to estimate the likelihood. And with Y given H prime, so that's the expected value. And at the current stage, what we know is H. So that's the current estimation of the parameters and the input X. So we don't really know Z, but that is part of the actual data. That's the E step. And yeah, so that's the E step. We want to, we estimate the Q H prime given H. And the maximization step is to replace the current hypothesis by the better one that maximize this Q function. So that's the conceptual kind of definition of what EM does. And so I just give you an example about what I mean about this general definition. So assume we have this image. So that's a very big gigapixel type of whole slide image. So what we want to do is we want to classify the type of tumor that's represented by this image. So it's a biopsy of the tumor section. And it can be, for example, 2 types of tumors. And then we want to do the classification to see which tumor type this one belongs to. So what we can do is we can use deep learning in this step. And so in short, we can just do a training. We can partition this image into patches, and then we give a label for each patch, and then we do the training. But so the objective here is we have the input image and the output label. But what we do not know is actually what label this should be, because we know this at the top level, we have the image level label. But for all the patches, we don't really have the patch-wise label. So the patch-wise label becomes actually the unknown parameters, or the Z here in this model. And the images are the X, the patch-wise label is Z, And the current parameters are just the parameters in this the training model. So what we want to do is, for example, at the E step, we can use, so we assume we have the model and the deep learning model for doing this classification. And so at the E step, we want to estimate all these unknown variables. So what we do is we can, based on the training model, we can derive the discriminative patches and non-discriminative patches. So discriminative means those patches that are actually useful in training this model. And some non-discriminative patches means those background patches that we don't really want to care. So at the expectation step, we choose the patches. So which are in fact, they are the unobserved variables in this model. And then once we have this estimation of these unobserved variables, then we can do the maximization step. So that's when we update the weights of this deep learning model. So we are actually updating the actual parameters within this deep learning model, and that's where we use maximization. So, and we can do this iteratively. So each time we are updating both the unobserved variables and also the parameters within the system. And so it's an alternative